wanted to thank the organizers for such a wonderful workshop. I'm learning a ton this week. All right, so today I'm going to talk about adaptive data collection for distribution shifts. And everything I talk about today is going to be based on joint works with my wonderful students, Namkoong and Tiffany. Namkoong's sitting over there. You can ask her the hard questions after the talk. And my former postdoc, Kelly, and of course, the inimitable, my colleague, Dan Russo at Columbia. All right, so in light of this excellent history lesson that Zaid gave, I don't think I need to provide as much context anymore. For those of you who know me, I sit at the interface between machine learning and operations research. And OR is a field that primarily studies the allocation of scarce resources, right? They've had to grapple with distribution shifts for decades, long before it became a mainstream topic in ML. So at the beginning of my PhD advisor, Peter Glynn, really pushed me to study algorithms, right, for specific distribution shifts. And I implemented some of these in production settings and industrial applications and so on. But at the end of the day, the bottleneck that I faced was my ability to specify distribution shifts, right, that actually aligns with what happens in practice, right? And then circa 2020, right, as Zaid was saying, Alec Radford and Jung-Wook Kim, when they came up with CLIP, right, it inspired many distribution shift researchers, including myself, that for tasks for which web data can actually be very helpful on, right, a lot of vision tasks, scaling data is perhaps the most obvious solution. Right? But of course, there's a lot of problems for which web data simply is not enough, right? So over the last few years, I've been advocating for a more inductive modeling approach, right, for coming up with distribution, for coming up with a language for distribution shifts, right? I think a key bottleneck that we have in the community right now is that we're still stuck at ID versus OOD, right? It's very difficult to describe the difference between different data sets and to understand which data set to go after next, right? And in the synthetic data world that we live in now, right, it could also be which next synthetic data to generate. And if we had a richer language for talking about distribution shifts, right, perhaps this interface could be more seamless. So today I'm going to talk about a new line of work I'm very excited about that really puts a central focus on uncertainty, what the current AI model doesn't know, okay, and how to allocate resources towards collecting data on these domains. Okay? So I'm going to first try to understand, right, how different the current data set is from what you saw during the training process, right? And I'm going to try to adaptively collect data in order to resolve this uncertainty in the future. And of course, active exploration, adaptive data collection, extremely classical ideas in reinforcement learning, right? And I'm going to really offer in some sense, a modern take on this. Now, taking a step back from distribution shifts, I don't want to pontificate too much in this talk, but perhaps just, let's just say that I'm a firm believer that intelligent agents, right, they must really truly comprehend what they do not know, right? And actually know how to take actions, make decisions to resolve this uncertainty. And over the last few decades, right, there's a lot of different research communities studying uncertainty quantification. And there's a ton of really, really exciting ideas in these literatures. But by and large, right, they haven't really truly scaled in the ML sense, right? In the sense that if you look at the Llama 3 report, you don't really see these ideas there, right? And my take on why, right, is that as an ML researcher, right, I actually know very, very little, right? In some sense, I only know two things. First, how to come up with a fictitious loss that I hit with SGD and optimize the hell out of on web scale data. And then in order to scale to web scale data, you've got to come up with a whole lot of different engineering innovations, and you test this via this game we play empirical benchmarking. And a lot of the previous ideas, I think, are pretty difficult to fit within this umbrella. And at least in my experience, ideas that don't neatly fit within this umbrella, it's been difficult to scale, right? So today I'm going to talk about how we can quantify, capture uncertainty, right, under these two pillars. The only two things I know how to do, right, as an ML researcher. And before I go there, let me first give you some background and set up some notation, right, for probabilistic modeling. Okay. So what is the typical approach to uncertainty quantification? Well, you try to model the environment, right? So you posit some parameter, right, that represents the environment, and you posit a distribution over that environment. And then you also have to come up with a data generating process. Okay, how your observations are generated under each environment you may expect to see in the wild. Okay? And then as you gather data at test time, right, you make inferences, posterior beliefs, right, on what the environment might look like. Okay, this is your good old Bayesian model. For the distribution shift domain adaptation people in the room, right, think of you as maybe some featureization of your data set. Now, I'm going to use a fake but real sounding example to illustrate why this is actually somewhat difficult to do in practice, right? So here, let's think about mental health disease diagnosis, okay? So here, the data that we have is a bunch of questions and answers with patients. And I want to diagnose, say, the probability that this person is schizophrenic or bipolar, and so on and so forth. Okay? Lots of things you might be interested in. Now, what is a latent parameter in this setting? Well, it could be described verbally as the mental health state of the person I'm talking to. There, okay, yes. Which could all go into this, right? And the whole point here is that this concept, it's devoid of physical meaning, right? It could involve genetics, right? It could also involve a lot of other things that happened in this person's life. And it's really a unicorn. It's very difficult to pin down, right, what the right notion of you to write down is. So Bayesian modeling, right, is as much an art as it is science right now. And if you master this art, you can do a whole lot of useful things. And people do this all the time in statistics, right? But in ML, right, we try to scale things up using massive historical data. And this is somewhat difficult to do, right? Because I can't really check whether these models are good or not. Okay. So in order to fit this idea of probabilistic modeling, right, into the two things I know as an ML researcher, I'm going to go back to the 1920s, back to Bruno De Finetti. Okay. So De Finetti was, I guess, one of the OG probabilists who really advocated for a different view of uncertainty. He really wanted to view the world, right, as uncertainty coming from data that you haven't observed yet, instead of these latent parameters devoid of physical meaning. And in particular, the famous De Finetti's theorem says that if your data is exchangeable, then the autoregressive probabilities, right, the probabilities that describe conditional on seeing things you've seen in the past, what do you think the patient's going to say next, right? That probability, if you can specify all of them, you can actually come up with a coherent Bayesian model. Now, just as an aside, maybe a context, I was taught stats at Stanford, and while I was taught for the stats PhDs in the room, while I learned the Hewitt-Savage 0-1 law and tail sigma algebras, I never really had a chance to sit down and internalize De Finetti's message, right? So let me just, you guys laughing because we took the same classes. So let me just say as an aside that Bayesians, right, they view data sets as being exchangeable. What do I mean by that? If I look at my notation here, right, the things that you observe are the x and y's, right? And the you never observe by definition. So if you marginalize that out, the x comma y's, they depend on each other, right, through the latent environment that they share, right? So these x comma y pairs, right, they become exchangeable rather than IID. Okay? For the more ML-minded people in the room, think of you as some featureization of a distribution. Let me pause here in case there's any questions, clarification questions on De Finetti's idea.
So, like, isn't exchangeable like kind of breaking the time dependence in a way?
It does, definitely does. And you can only model very, very partial time dependence. It has to be basically like a recurrent Markov chain. That's why I intentionally picked the question and answer example in my fake example. Okay, so if you look at the stats literature that takes Definetti's perspective to Bayesian modeling, right? They use basically human intuition to specify these autoregressive probabilities, right? Using copy laws or different different one-step parameterizations. Today, Martin.
Can you clarify what you mean by uncertainty? Because it can mean many different things.
Yes.
Context.
Good. Here, uncertainty, I'm being intentionally vague because I'm gonna clarify all of this in the context of a particular decision-making problem later on. For now, I just want to focus on delivering the high-level insight that Definetti had. But for the sake of next few slides, think about me wanting to quantify the probability that you have schizophrenia or bipolar, right? A number of different conditions that I might be interested in diagnosing. Does that make sense?
But mean estimate the conditional distribution, or does it mean quantify the uncertainty in an estimate?
Get the conditional distribution. Okay. Estimate the conditional distribution. And I'm not going to talk about the estimation error and uncertainty in that process. I'm just going to not talk about that at all. Okay, so instead of going about this by just specifying the autoregressive probabilities by hand, I'm going to, again, go back to the two things I know as an ML researcher. I'm going to utilize massive historical data to learn these autoregressive probabilities. Okay. I take a whole bunch of patients, right, and all the Q&As that I've had with this person, and I'm going to fit this probability using a neural net. And of course, the nice thing about this is that we actually know how to do this really, really, really well, right? As a community, we've mastered this art over the last 5 to 10 years. I actually want to get the probability of this person having schizophrenia or bipolar, a number of different conditions you might be interested in.
On the question and answers or based on other factors as well?
You can add in other contexts, for sure. That's why I say this is a fake example. You can add in as many features as you want here that you can actually measure and observe.
If I were to use this model, so that means I only depend on the question and answer specification on the
No, this framework actually trivially generalizes, and I will show you that later in the context of industrial applications that I'm actually familiar with. I know nothing about mental health. But I can imagine that, as you said, doctors might have a lot of prior information that they want to put in, right, as a part of this conditioning.
Because I would think in this case, the question and answer is a patient would be the least reliable.
Good. Okay, good. Maybe this is not an appropriate clinical example in that sense. Yes. I'm mostly trying to showcase Definetti's mathematical idea. All right. So let me continue this example, fake example, again, devoid of clinical practice, and talk about what Definetti meant, right? So let's say these are the real questions and answers that the doctor have actually seen with the patient, okay? And now I'm going to have an LLM simulate out the answers, right, for hypothetical questions that I can ask this person. And then I generate this long list of Q&As. I take this, say, a human expert or some rule-based system, and then I can calculate whether this person, right, has schizophrenia or not. But this was one rollout, one random realization, right? And you can do this again. I guess I have a typo. Simulation 2, right, is another rollout, just another autoregressive generation, right, along all of these different questions, and you get different answers. And again, if you put this through this black box, now this expert says that, oh, in fact, I don't think this person has schizophrenia. Now, what Definetti said is that the variation in these quantities, right, it's actually an accurate reflection of your posterior beliefs. Again, I know how to generate these out quite well.
That's right. Like you could have something else, some other version of the
Good. So here I am, I'm trying to show a schematic first and then math later. But yes, formally, there's a bunch of different questions that I can ask you of a very large bank, a typical unsupervised setup, right? And I simulate out all the different answers I might have seen in an autoregressive way, right? So this is, again, one rollout, another rollout, and the variation in your probability of having schizophrenia, right? It's entirely determined, as you exactly said, about with the variation in the rollouts. One thing I want to highlight here is that the nice thing about this, right, is that it's actually a Bayesian model in the sense that if you have seen different sets of real questions and answers, right, let's say here I have a different set of questions, then your rollouts are going to look different, right? And in this case, maybe in most rollouts, you conclude that this person has schizophrenia, right? In this case, you have very low uncertainty. Did everyone understand Definiti's high-level insight at this rough, vague level before I formalize everything?
data. Like
I am, yes. So as I started the talk with, I am assuming that you have access to massive historical data, web-scale data, over which you can train these types of sequence models. And I'd like to, in some sense, shove in the paradigm of quantifying uncertainty, right, into the two things I know how to do as an ML person. And if you don't have this massive data, it's all moot, right? That's why I began with this, in some sense, the disclaimer, right, that in those types of cases, you got to do more gourmet modeling, which I also like and advocate for in most settings. But today, I'm going to be an ML person.
sorry, just to understand, I'm by the web scale analogy, and partly because like web data is not a reflection of life, right?
Yes, for sure.
Are you assuming that when you say web scale data, data that is a reflection of
Yes.
reality?
Yeah. So what Martin was asking about also, right, is that how do you actually get the sequence model, right? And you're never really gonna get this magically. And this is, again, I fully resonate with this. And I'm usually the person asking these questions in most rooms. But my bottleneck has really been that even when you have this data, I don't really know what to do. And I'm gonna show an application where you actually do, right? And if this is possible, then I think I can then, someone gave me $5 billion, right? I can get a lot of smart people in the room and then carefully think about what data do I collect, which I think is what OpenAI is doing currently. While I'm in this mode of explaining Definiti's insight, I really want to highlight one thing, which I think is a common confusion in the literature, which is that you really got to autoregressively simulate out. Okay? If you predict the answer, given the real stuff you've seen for the next question, and then you do the same thing independently for a different question, this doesn't work. You really gotta predict the answer to the next question, put that back into the context, and then predict the answer to the next question, and repeat. This is really what allows you to differentiate between epistemic and aleatoric uncertainty. And the long list of papers here, the main thing I want to say here is that I did not come up with this insight. It's been known since 1920s. I did not know it until a year ago. Okay. And the past year has been me grappling with this insight and turning it into ML algorithms of different sorts, right? So naturally, a ton of people knew this. If you think about Bayesian statistics carefully, I'm pretty sure you already knew this. Okay. So now I'm going to bring out the OR person in me, and I'm going to answer Kamal's question, which is, when do you actually have this data set, right? So now I'm going to go to recommendation systems. Now, the thing about the Rexis literature is that the cold start problem, right? It's universal. You always see new users, new items. But you do have to be careful about collecting data, right, in a mindful way. And prior to LLMs, we didn't really have a way to get a very grounded understanding of content, right? So as a result, we learned all of these content features, right, through collaborative filtering, right, two-tower models and so on and so forth. But now we actually have a chance to use LLMs, right, and have them watch a new movie on Netflix to understand whether Rich is going to like this movie or not, right? So just as an illustration, right, of the potentials of us being able to do this, but also to illustrate that this is not a magic bullet, right? Let me show this video. All right, so out of context, this is such a random video, but apparently it went viral on TikTok a few months ago, right? Now, imagine having an LLM watch this video. Would you have foreseen that this video would go viral and have tried to push this to different users? Well, if I was the LLM, I certainly couldn't have, right? So what I'm trying to illustrate here, right, is that in addition to the video features, right, even when I can actually have the full ability to comprehend the video, there's still remnant uncertainty that I got to grapple with. The only way I'm going to resolve this uncertainty is to show this to a bunch of different people, right? I can show this to Kaizong, and maybe he likes it, but Rich doesn't, right? And this is how I understand people's preferences when it comes to the latent factor for this video. You don't like it? It's all right. You got to keep up with the times, Rich.
Actually, one of the
Okay.
but you have to watch the entire thing to understand it. It's just like these guys just having fun.
Okay.
So to bring this insight to bear, I'm gonna give a motivating setup here of news recommendation, right? So this is, I think, a very nice illustration of the code star problem that is so common across Rexis, right? Because newspapers appear all the time, right? Every single day, right? New items come up every day. And I got to understand, right, which people are going to like which newspapers. So I want to have an LLM read these newspapers to form some informed prior. And then based on this, I want to do active exploration, something like Thompson sampling. And I'm going to do this every single day, right? And I have done this for a while, if you're a newspaper company. Oh, you're good. All right. So again, the thing I want to do is every day when the articles are released, I want to have an LLM form an informed prior on how good you think the article or that video looks like based on the features you can have access to based on the content alone. And then systematically, you're going to start showing this to different people to resolve your uncertainty, right? And I think this is really the key to intelligence more broadly, right? Again, without pontificating too much, I think we really need the ability to sharpen beliefs as you gather more data, right? And the ability to decide how to gather this new data in order to maximally sharpen your beliefs. For the more mathematically oriented people in the room, for the rest of the talk, I'm going to assume that the users are entirely exchangeable on this platform. Although everything I say generalized trivially to settings where each user has their own feature. Okay. How many of you have not heard of Thompson sampling? Silly way to ask the question. So Thompson sampling is basically perhaps one of the most popular active exploration algorithms, right? And the whole point of this is to be optimistic under uncertainty, right? So if you have an article, the blue article, where you're really not sure how good this article is, like the video, you better show it to Kaizong and Rich to see whether they like it, right? That's the whole point of exploration in bandits and RL, okay? And like before, I'm using you to denote everything you do not know about how viral this video is going to be, even after having watched it. Okay. Does everyone follow my notation so far? Now, if you want to apply Thompson sampling in the setting, right, the primary challenge is that you have to somehow come up with a informed prior in the space of text, right? and then have the ability to sharpen your beliefs to posterior updates as you gather more data. Right? This is pretty hard. Some people might be able to do this, but I certainly can't. So my solution today is going to be leveraging massive historical data. Right? So what I'm going to take is this entire historical data, and I'm going to train the sequence model that I was talking about earlier. And I'm going to use that sequence model to run Thompson sampling. Okay. First, I'm going to think of my historical data as this gigantic table, right? The Z's are everything I know about the article without having shown it to anyone, right? This is similar to things I know about the patient without having first talked to the patient. And then these are all the different user outcomes, whether they liked this article, whether they shared it, right, whether they commented on this, so on and so forth, right? And this is Rich, this is Kaizong's one, on and on it goes, right? So I have this gigantic table. I'm going to view each row as a sequence, right? I'm going to fit a transformer on this. You can view Z as a prefix, right? You can do cross-attention. There's a lot of different architectures you can use. But in any case, right, I can validate all of these different architectures on the val loss, right, by masking some of these different things that I could have seen but did not observe. And just to give you some intuition, right, I think a lot of people these days understand how in-context learning is kind of similar to Bayesian reasoning, right? And I think a lot of this started with Percy's paper a few years back. And intuitively, if you have a good sequence predictor, you should be able to make a prediction of Y after having seen 2 data points. And you should be able to make sharper predictions after having seen a lot, right? And Definity's insight is basically that this, right, the ability to predict observables is actually sufficient for characterizing uncertainty, epistemic uncertainty on latent factors. So now I have this transformer. Okay. Let's say that I did my job as an ML person. I somehow came up with this sequence model. How do I use it at decision time? Well, for any new articles that appear today, okay, sorry, this is a typo. This should be an A here instead of K. For this first article, I have 2 people who watched this so far, who read this so far. And then these are stuff I autoregressively generate, imagined data. Okay. The last one, I have only recommended this to 1 person before. I only have 1 data point. I simulate out the rest. And then using this fake data, I'm going to calculate, say, the average click-through rate. So these are imagined average click-through rates. And then I'm going to pick the best article, recommend that to you. Okay. And the main intuition here, right, is that because I'm generating these in a random way, right, articles that you're uncertain about, they actually have a chance of being selected because of that variation. And going back to Definity's insight, right? For those of you who already know Thompson sampling, the scheme is precisely Thompson sampling, optimizing your action under a particular posterior draw, right? Where instead of doing a posterior draw, I'm generating missing data, right? Again, Definity's view of uncertainty coming from missing data rather than drawing on a latent factor from some posterior. I think I saw a hand up somewhere.
I don't understand the structure of the sequence. Users are exchangeable. So what's the context even if you can exchange all the users?
So the real version of this is going to look like, do you know what 2-tower models are? Do you know what 2-tower models are? So in Rexis, the most common architecture for learning content and user embeddings is basically to implement collaborative filtering using neural nets. And you try to featureize you and the videos that you've watched on YouTube, right, in a way that they align well in some embedding space. right? So these are basically user and feature item embeddings, right? So in some sense, this is everything you know, right, about the person and the video before even doing this online exploration. So all of these people are going to be endowed, right, with these features. And all of this effectively generalizes. Happy to talk about it offline.
You're modeling the Ys as an autoregressive, like ordered set or like a sequence, right? But technically they're not. Is the point of the order so that across different samples it's the same person's opinion, so that it like stays the like keeps the correspondence? So, yeah. The
ordering doesn't matter. What I should actually say is set modeling instead of sequence modeling, right? The exchangeability, right, means that the ordering doesn't matter. So the mathematically proper version of this, right, actually leverages the permutation invariance. So when we actually do this in practice, we augment, we permute and do all these different things. There's a more subtle question of how do you make self-attention permutation invariant, right? Because if you simply remove all the positional embeddings, then it can't actually differentiate between X and Y. There's all these different details that we actually go into in Namkoong's paper. She's over there and we can chat after.
But one thing, if you remove the dependence, then it won't capture the vertical, like, because the, each person has a profile, I assume, like Y, then, Y1 might get matched to Y2 in the next.
But the X comma Ys are exchangeable, right? Okay. So you put the right X in, so you can deal with all of this trivially.
Yeah, so sorry for keeping on our work. So you try to resolve uncertainty, but I don't see how you generate, things to replace the missing data.
Good. Yes. Yes. So this is why I asked if people have heard of Thompson sampling. I personally am not a firm believer in this, but a prominent way of resolving uncertainty is via this very greedy heuristic called Thompson sampling. So here I'm mostly illustrating that Definity's idea can actually power Thompson sampling, which is in some sense some of the more prominent exploration methods that I see in industry. I think the intellectually proper version of this, and I'm going to get to this maybe in the final slide of this talk, is to view this as rollouts, right? And this rollout is a posterior draw, right? So what I now have is in some sense a posterior belief that updates over time. And I can view these beliefs as the states of a Markov decision process, right? And then I can actually put on an OR hat and say, how do I solve this dynamic program? And you can come up with all kinds of different planning algorithms for resolving uncertainty, where the states of this planning algorithm, right, are your posterior beliefs. So this is, I think, what the proper way to do this. I have a couple of papers exploring related directions. Happy to chat offline. But you're entirely right that I am taking on faith, right, that all the different regret bounds that people have shown for Thompson sampling effectively say why taking this maximum is actually kosher. How much time do I have? 8 minutes. Cool. Okay. Any questions about the algorithm itself?
You're leveraging the uncertainty in your empirical estimates for the farm. And so here, if you have an idea how you choose the number t, because if you choose the t to be very small, then you kind of get it to the sampling, but if t is super large, then those fields will be concentrated.
So actually, t needs to be infinity for this to be Thompson sampling, the opposite. If t is small, then you're conflating aleatoric and epistemic uncertainty. So imagine like a beta Bernoulli Thompson sampling, right? The aleatoric uncertainty is the uncertainty in the Bernoulli, right? The coin flips. Epistemic is the uncertainty in the click-through rates, right? So in order for me to actually claim that Definity's insight is legit, right? Then t needs to be extremely large so that the law of large numbers for exchangeable sequences kick in, right? And that this has actually converged to the population click-through rate. So if you look at the typical large law of large numbers for exchangeable sequences, then you get the usual 1/square root of t style rates. I think there is still a lot to be done in terms of uniform convergence and so on. But by and large, my current rough impression is that stuff that I know about empirical processes, the basic ones, kind of generalize to exchangeable sequences. So that's sort of the scale at which t should be in if you want everything to be entirely legit. But of course, I'm also not talking about test time compute, right? And this is actually not practical, right? So this is not real right now. That's why I keep saying it's an intellectual idea. I think it's a really fun one that potentially has maybe I can scale.
Just a matter of updating the release based on what you observe, based on them, that changes the uncertainty.
Right.
Now, what if these Y1 to YKs are not what if there are
Right. Right. So basically, you can incorporate features into this, and that the way to think about it is you're going to do this separately for different feature groups, right? The way people do this in ML is to featureize you as a person using some continuous feature. Yeah, so you're going to cross that. But then the where this actually, so that's all fine, right? So that's sort of what the straightforward generalization of this to typical Rexus settings. Where this actually breaks is if you transpose this matrix, in the sense that if these are actually users and all the actions I take, right, on Instagram, there's no way they're exchangeable, right? No matter how much you featureize it. In this case, all of the math breaks, right? But I actually still think that if you think about O1 reasoning, right, it does rollouts, and I think it does some notion of tree search, right? Which is a particular type of a planning algorithm based on rollouts. So I feel like this way of thinking actually extends quite far beyond the narrow exchangeable setting. But I'm mostly illustrating this idea in the context of this rigid setting. Well, first, because it's Simon's, but second, because I think it actually clarifies this insight a great deal. Does that answer your question?
I mean, maybe I am missing something in the previous examples, right? The setting that you are talking about here is a single prediction, and there, you know, like there's annotation.
I'm sorry, can you say the first part of your?
It's a single prediction, right? Like, is this person going to like this thing or not? Like,
Yes.
one way,
Yes.
right? There I can see there is alloteric uncertainty and epistemic uncertainty. It's clear what that means. But when you talk about something like O1 and reasoning, it's unclear, right? Like your question may be specified. There might be other things going on. So, you know, so yes,
that's why I'm not writing this down in my slides, nor do I have papers on them, nor do I have theorems on them, right? This is me pontificating in response to that. Okay. I am totally with you, yes. Okay, so this is me trying to be a good scholar, right, and writing down all the assumptions under which these things hold. Exchangeability, again, is the key thing, right? And as Malik was noting, this doesn't happen, right, in these other examples that I was pontificating about. These other two stuff, basically ignore them. For those of you who know what confounding is, right, basically the assumptions you think have to be true in order for some of these things to be legit, they have to be true. So the main theorem, right, basically says that the regret of this algorithm, the Bayesian regret of this algorithm, averaged over days, right, is comparable to the regret of Thompson sampling that actually uses the correct informed prior over Z's, the text features, up to the good old perplexity, the sequence prediction loss, that we build scaling laws over. Okay? So your prediction error actually controls online decision-making performance. And what this means is that I can go to YouTube, right, TikTok or Instagram, and if I build scaling laws with respect to user interaction, right, that scaling law is actually going to govern my ability to solve the code start problem for recommendation systems. Let's hear again. Why? What?
Where was it created? Where this came from? So
This is what people build scaling laws on, this exact quantity, the sequence prediction laws.
So it's referring to the training scale. Like what kind of scaling law?
The not inference scaling law, training scaling law. Yes, the regular vanilla scaling laws. Yes. Okay, and the proof of this is actually quite interesting. Happy to go into this offline if any of you are interested. All right, so I'm gonna basically show you like a very, very simple proof of concept, right, that I can do within the confines of academic data. Okay, so what I'm gonna do, right, is come up with a really, really simple architecture for combining the Ys with the article headlines. Okay, I'm just gonna use BERT, and I'm gonna train this entire thing, right, to do sequence predictions. And then let me first put on a stat set and show you coverage, right? When I say this is a 95% credible interval, is it actually? Okay, so here are the y equals to x line. This is what it should be. This is what it actually is. Y equals x is perfect, right? The reason I'm showing you this plot is obviously because the stuff I presented is very close to y given x, right? So that part's fine. But what I actually want to focus on is ensembling. So the state of the art, and in some sense, the only thing that we have in our toolkit, right, when it comes to scalable and certain quantification is ensembling or bootstrapping in practice. Okay? So you can try to do this when you have 0 observations, meaning no interaction so far for this article. And you can see that it undercovers quite a bit. And even worse, the problem with ensembling is that it's really, really hard to do posterior updates as you gather more data. You've got to somehow update each and every particle of your ensemble, which is not an easy thing to do in practice. So now, given this, right, calibrated probabilistic estimates, you can now take this to a Microsoft news article recommendation data set where you actually see the impression data. And you can see that here, knowing being able to actually comprehend the article features, it does matter a little bit, right? Not too much because the headlines I think are still pretty simple, but I am at least unaware of academic data sets in which I can showcase this. So if any of you have ideas, I'm all ears, and I think there's a lot of interesting empirical benchmarking exercises to do in this arena. Okay, so let me actually end by pitching my overall vision, which is that I think going beyond web data, right, as reflected in many of the questions you asked today, really requires careful data curation, right? And OpenAI, Anthropic, they have entire organizations whose job is to think about GPT-K+1 and what data to collect and so on, right? And this is what I meant by we need a new language for talking about distribution shifts, right? Entire data sets. And I'd like to train models that are capable of formulating some informed prior, right? And actually adaptively deciding which data to collect subject to cost constraints, right? And then based on it, you're gonna do a posterior update. And I think Definiti's insight actually maybe gives you a reasonable recipe for doing this, right? You view the sequence model as in some sense a probabilistic simulator, and every rollout you do is in some sense a posterior draw, right? And the variations in these rollouts are basically your epistemic uncertainty. And what's really nice is that this is actually an auto-differentiable simulator. So you can apply differentiable planning algorithms as opposed to these discrete search methods like MCTS. Okay. And again, the main thing I want to highlight is that the really nice thing about this regime is that I don't really need to worry about whether MC-MC converged and stuff like that. Because if I collect more data, now I just put that into the context of the transformer, right? It's as simple as that. All right, I think I'm out of time, so thanks a lot for your attention. Happy to take any additional questions.
One very quick question. Basically, we already had enough questions. Let's take start with the